All right. Good morning, everyone. And today we're going to continue our conversation about combinational minimization. We talked about K-map, which works pretty well for 4 variables. It's a big match for anything more than 4 variables. We talked about the Cohen-McCluskey algorithm, which can work with any number of variables, but it's also a lot of calculation. You need to deal with so many binary numbers, do all the combination, tabulation, parameter charts, go through multiple steps to find minimal cover. And today we're going to see a solution called map into variable to allow you to deal with 5, 6, 7 variables in a K-map format. And after that, we're going to see how to design circuits more than a 2-level SOP or POS. 2-level POS, SOP are all we have seen so far. And we're going to see some alternative formats. All right. So before we start, I'm going to play a video.
Most people, when they think of origami, think, my 8-year-old is doing origami. Why are these engineers at BYU working with origami? Why are these the device from things like bending and deflection instead of hinges and bearings, and we can actually sometimes it can also operate in very harsh environments like the environments.
Origami helps inspire new ways of looking
at the space. And the nice thing
the panel hanging behind the scale prototype. Much larger array into space. Spacecraft would be inside a rocket like an LS-5 rocket, and the solar array would wrap around the outside of the spacecraft. And it would be all folded up compactly and then launched. This is our CubeSat version as we open it. It opens to about 50 centimeters and has the potential to generate about 65 watts of energy at this actual size. CubeSats are kind of the new novel way of getting things into space quickly because they're small, they don't cost a lot, and you can throw them on with any rocket that's going into space.
In addition to working with people like the National Science Foundation, we have projects with NASA Marshall Space Flight Center in Alabama, and also with JPL. These are the same people that do the Mars rover and other things. We are doing origami inspired mechanisms, the expanding solar array. We're involved.
All right. So essentially, origami is a way where you can fold it up, fold that solar panel before sending it to the space, and then expand it when you need it for utility. And today we're going to see origami for K-map. Essentially a way to fit a larger function into a smaller K-map. You can put 5 variable, 6 variable, even 7, 8 variable function in a 4 variable K-map. All right. So all right, so this is the first diagram I showed you about a K-map. A K-map is a way to switch the orders compared to a Vich chart so that you get all the adjacencies by including also this wraparound adjacency. Right? And 4 variable K-maps is pretty elegant. 5 variable K-map, 6 variable, they are doable in the book, but they are a big mess. So the topic for today's class is how can origami help in using K-map to represent larger functions. And in particular, we're going to try to fold up a bigger function for representation, and then we'll unfold it to solve the minimization problem. All right. So what do I mean by folding? So here's a 3 variable K-map. By folding, I mean to get rid of one of the variables. And right now, I pick one axis. And on the left side of the axis, I have a equals 0. On the right-hand side, I have a equals 1. So I'm really folding based on the a variable. So what I can do with that is I can really create 2 separate K-maps. So this K-map is really a BC K-map when a equals 0. This is a BC K-map when a equals 1. What I can do is I can fold them up into a single K-map. So whenever B equals 0, C equals 0, which are these two positions, right? The output is just 0, so you can put that as a 0 in the folded K-map. And then if you look at these two positions, that is when B equals 1, C equals 0, output is just 1, independent of the A variable. Things work pretty well until you run into these bottom cases. The next case that we need to address is when the output is 0 when A equals 0, output is 1 when A equals 1. We just cannot represent that using a single literal in the regular K-map. And that is really what the map-entered variable method is trying to address. The MEV method identifies these kind of conflicting cases when you have 0, when A equals 0, 1, when A equals 1, and then create a new variable and put that variable in the K-map. So now in addition to 0, 1, x, you can now also put variable as a cell, the value inside a K-map cell. And this value will indicate that when A equals 0, output is 0, when A equals 1, output is 1. So really that is a function, f equals A, that will be evaluated when you have B equals 0, C equals 1. Sometimes B, C value by themselves can determine the output value. So those are shown as a constant 0 or a constant 1. But if they disagree, the output depends on A. So just put down a variable over there. And in the other case, when A equals 0, output is 1, A equals 1, output is 0. So output is essentially the complement of A when B and C are both 1s. So we put down a variable A prime in the K-map. Yeah. Does it make sense? Yeah. Any questions? All right. You see with this method, now we can represent the very same function instead of a 3-variable K-map in a 2-variable K-map. Right? In general, we can apply this method to fit in larger function into a smaller K-map. All right. You can fold a K-map multiple times by any variables you like. Let's say in this K-map, this is a 4-variable K-map based on A, B, C, D. You can fold it by A, essentially creating a cut line. On one side, you have A equals 0. On the other side, you have A equals 1. And what I mean by folding is really, I will fold the 1 side to the 0 side. Right? So think of this as a piece of paper, and then you fold it across the middle. So these two cells really have the same B, C, D value. They have different A values, right? But they have the same B equals 1, C equals 1, D equals 1. So these two will be merged into a single cell. Similarly, let's say these two corners, when you fold them up, they will overlay on top of each other. So they share the same BCD conditions. And if they agree with each other, let's say when you have this constant 0 over here, they can be folded into a single value of 0. You have the 2 1s here. They can be represented as an output of 1, again, independent of that folded variable. And they just agree with each other at many other positions, right? These are all 0s, these are all 1s, and they become the 0s and 1s in the folded K-map. Again, now with only BCD, you can essentially represent the function with the additional help of the map-entered variable. So these positions, the output depends on A. A equals 0, output is 0, A equals 1, output is 1. So you represent them as a variable A in the folded K-map. That's to fold it once on the A variable. You can also choose to fold it using other variables, right? You can draw a different line. So let's say you can draw a line over here, and then fold the bottom side up. We always fold the 1 side to the 0 side, so that things follow that increasing Hamming order: 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Right? If you fold this to the other side, you have like 1 column over here, 0 column over there, which is a little bit different from how we usually write K-maps. Right? So the fold line is really up to your choice. So this folded K-map can actually be further folded. You can pick another line. Let's say I pick another line of C equals 0 on top, C equals 1 at the bottom. And then I can fold it one more time. First, I'll find these common values, 0, 0. These are all 1s. Again, when you fold them up, they'll sit on top of each other. So if they have the same value, they can be represented by a constant in the folded K-map. Right? And these two positions are both A's, which means in the folded K-map, the output is also just A. 0 and 0 can be folded into 0, 1, 1 folded into 1, A can be folded into a letter, the variable A. And finally, we have this disagreeing 0 and 1. We need to look for the condition for that folded variable. So the top line has C equals 0, bottom line has C equals 1. So again, the output is just the C variable. Right. Now we have just represented a 4-variable function in a 2-variable K-map. We reduced 2 dimensions. Right. So this is what NASA did to their sunshade, a way to deploy a solar panel into the space. They first fold it up for compactness of storage, and then put that into a rocket and then send it to the space before unfolding it for utility. Right. So with K-map, we have just seen the folding process, a way to represent the function in a smaller space, right, in a smaller K-map. But at some point, we also have to unfold it to get the utility out of it, to find the minimal expression of a function. Right, so that's the second part of the question we need to address, how to unfold this MEV K-map to find minimal expression. To do unfolding, let me spend 1 minute explaining different variables in this K-map again. If you see a 0, that means output is 0 independent of the map entered variable, independent of this variable that you use as a map entry. If you see a 1 in a K-map, that means output is just 1 based on these 3 variables independent of D. If you see an X, that means we don't care the output regardless of the MEV. If you see this map entered variable, that means the output depends on this additional variable. Right. So we can say folding is just the opposite of unfolding. That's a pretty intuitive explanation. We just apply the reverse process to get a larger K-map. Right. So in this example, what we can do is, we could unfold this single 0 into 2 zeros here and there. Again, I think of this as a folded piece of paper, and then when I've unfolded, this 0 becomes the top left corner and top right corner. Next 0 becomes 0, 0. Right, essentially this bottom 0 becomes 0, 0. These 2 1s become 1, 1, 1, 1. And the X remains X. So D means output equals D. So when D equals 0 on the left-hand side, my output is 0. When D is 1 on the right-hand side, my output is 1. Right. Similarly, for the bottom D, on the 0 side, the output is 0. On the 1 side, output is 1. So the output, what I put in that expanded K-map, depends on the value of the D. D equals 0, D equals 1. The output is 0 and 1 respectively. But effectively, until this point, we have done nothing. We came from that K-map to fold it up, and then we unfold it, essentially getting back to the original K-map. But the only scenario that you would want to use map and the variable is because you cannot unfold it. You do not have a big enough K-map to represent this unfolded function. So really, what I'm doing here is cheating. In general, we use MEV because we cannot represent the function fully in a K-map. And therefore, we somehow have to find a way to do logic minimization without a bigger K-map. Essentially, do minimization within this 4x2 K-map. Right? And that's a question we'll address. How to do logic minimization? Essentially, the same idea of essential prime implicants, without fully expanding the function into a larger K-map. Yeah. Any questions? All right. So the goal is to find the minimal SOP of a function from this K-map. And one thing that is worth pondering is that the function can always be written as a sum of terms. And some of these terms will not depend on that map entered variable. Some of those terms will depend on the map entered variable. We can always decompose a function into those 2 classes of terms. So sometimes maybe all of the terms depend on D. Sometimes maybe all of the terms do not depend on D. But we can always categorize the implicants into these two categories. Right? These two categories covers all possible implicants with D or without that additional variable. We have just broken down this large problem into two smaller problems. Now that given this categorization, we can first find all the prime implicants that do not depend on the map-enter variable, everything that does not have that additional D variable. And then we can use a separate method to find all the product terms, all the prime implicants that depend on the map-enter variable. Again, this big problem has been decomposed into two smaller problems. Some of them depending on the MEV, some of them that do not. All right. So in this example, I need to find some product terms, some implicants that do not depend on the D variable. So to do that, essentially I focus on my minterms, the minterms that are shown as ones in the K-map. These are the minterms that are definitely minterms, just dependent on ABC. Right? Once you assign some values for ABC, these minterms will produce an output of 1. So essentially, by ignoring the map-entered variable and only looking for implicants based on the minterms, I can find some term, in this case, A prime C, as one of the prime implicant that does not depend on the D variable. And that is one thing I need to include in my minimal expression. You see at the bottom, I have A prime C. And that is an implicant that does not depend on the MEV, which can be found by just ignoring the map-entered variable in the K-map. Right? Setting D to 0, ignoring them, and then you get to find some of these implicants that do not depend on the MEV. And on the other hand, if you're looking for those terms that depend on the MEV, what you can do is you can treat the MEV to be 1 to encourage finding more implicants based on those MEV. So essentially, this cell will be 1 only if D equals 1. But when you're looking for implicants that are dependent on D, you're going to multiply it by D, and therefore D will be 1. So we can set D to be 1 in this K-map, right? Create a different copy of the K-map by putting D to be 1. And then at the same time, we're also setting 1 to don't cares. Right? Does anybody know why we're setting the minterms to don't cares in that K-map when finding these D-dependent implicants? OK, so before that, is it OK if I put them as 1s? Do I still get a valid solution by treating them as 1s? Right. Again, the goal for this K-map is to find all the D-independent implicants. From this K-map is to find all the D-dependent K-maps. Do you think we can just keep minterms to be 1s in this K-map? Yes. Okay. Yes. Yeah, exactly. If you keep them as 1s, you could get some redundant terms because these minterms have already been covered in the D-independent case. So any implicants we find from this table will just stay in the original form, like A prime C, and be stored in the final expression. If we keep them as 1s, we could have covered them again, but anything that covers them will be multiplied by the D variable, because that is a K-map where we will use to find D-dependent implicants. So anything that we find from that K-map based on ABC will be multiplied by D. So we could, in some situations, get some redundant terms, some terms that can be absorbed by a bigger one if we treat them as 1s. Even though in this case, when we treat them as don't cares, eventually the minimal expression will set them to be a 1. So it doesn't really matter for this particular case. But in general, right, because those two minterms have already been covered without the D variable, if you cover them again and then multiply the product with a D, it's going to be a smaller product. Right. So let's say we treat the 1s as don't cares, and then we find the minimal expression, essentially all the prime implicants. from this other K-map, right, which forms the minimum covered, then anything I found in that K-map need to be multiplied by D. Right? I have C times D, A prime B times D. The reason? Well, I set D to be a 1 in that case. Essentially, I assume D to be true. So for any of those implicants to be valid, D has to be a 1. Right. So again, now you see, with this 3-variable K-map, we essentially optimized a 4-variable function. Yes?
Why you made them, but why did you do it in that?
You cannot. All right, and here's the reason. So on the left K-map, we're trying to find the D independent implicants. If you treat these ones as x's, they may not get covered in the K-map. Actually, the minimum expression is nothing in the K-map. And anything you find in the K-map will be multiplied by D. So you will never be able to get the term A prime C that is needed for the minimum expression. So essentially, those mean terms, they must be covered in the D independent case. The reason is actually because anything that you can find over here is a superset of this K-map. This one, any mean term or any implicant will stay in the original form. Everything over here will be multiplied by D. So if you have a choice between the two K-maps, you want to cover the mean terms in that D independent case. We're going to see a more complex example later with both D and D prime, and actually over there, the picture is slightly different. Yeah, any other questions? So this is the first example. In a 3-variable function, we minimize a 4-variable. In a 3-variable K-map, we minimize a 4-variable function. And as I promised you, we can handle a bit more variables using MEV. You can also put 2 separate map hunter variables in a K-map. Now you have a 4-variable K-map for a 6-variable function. The function depends on A, B, C, D, E, F. And in this case, E and F become your map hunter variables. And again, for all the mean terms, because they can be covered without dependent on E or F, we can set E and F, both of them, to be 0, and then just focus on the mean terms appearing in the 4-variable K-map. And that is the first K-map you get, the EF independent K-map. And again, our goal is to find the minimal expression from there, essentially a set of implicants for that function. And that will be part of my final expression. And then I'm going to looking for everything that depends on E, and then everything that depends on F using 2 separate K-maps. In that E dependent K-map, I need to set E to be 1, so that these things get covered when I multiply the implicants over there by the E variable. And again, I set all the 1s to be don't cares. Again, because the 1s have already been covered in the EF independent K-map. Right? Those 1s have already been covered, so you could cover them again, but you don't have to. Again, then I find the minimum expression from the second K-map, but remember that is an E-dependent K-map, so you need to multiply anything you find over here by the E variable. And finally, in the F-dependent K-map, I'll set F to be a 1, because the output is 1 when F equals 1, and any implicant I find over there that goes into its minimum expression will be multiplied by F. And you just collect all the implicants, which give you a minimum expression for the overall function. Remember here, we're trying to find the minimum expression from each individual K-map. And then if it depends on one of the MEV, I need to multiply the expression by the corresponding variable. Yes?
So we don't need
That's right. You don't have to worry about the case when both of them are 1s. Right? Essentially, in the first K-map, both of them are 0. Right? Second K-map, E equals 1, F equals 0. Third K-map, E equals 0, F equals 1. We're missing that case of EF both being 1s. And the reason is because in this K-map, these entries that depend on E and the entries that depend on F are, they happen at different positions. MEV, map-entered variable, is only one way of having map-entered something. You could also have map-entered functions, something that depends on both E and F. But by the definition of map-entered variable, each variable depends on only one of the MEV variables. So the impact of E and F never happen on the same position. So it would never have a case that depends on both E and F. And if you choose to create a new K-map, E equals 1, F equals 1, 1 equals X, anything you find over there will be a subset of what you already found in the E-dependent or F-dependent K-map. So see, with this method, we're not only getting a correct expression, we're also getting the minimal expression. And that is really because E and F are two independent variables. They have impacts on different conditions based on ABCD. All right, I think I've said enough. And here's an exercise for you. We're going to spend quite a few minutes on this exercise. So now this is a new example with both A and A prime as map-entered variables. Right? What do I mean by A prime? Well, A prime means the output is 1 when A equals 0. Output is 0 when A equals 1. So output is the complement of the A value. Right? Things get shown in the BC K-map. So I'll give you a few minutes to work out those three separate K-maps, right, for different scenarios, dependent, independent, and then try to construct a minimal expression using some unfolding method by giving assignments to each and every variable in the original K-map. So probably call the first one independent. The second one depend on A. The third one depend on A prime. I'll give you 3 minutes to work on this exercise, and then I'll walk through the room, and then let me know if you need any help or clarification. And then I'll ask you to discuss with some other people in the classroom to see what you find, or if there's any challenge that you encountered. Yeah, if anyone needs a bit of help, just let me know. Yes. Yeah. Yeah, feel free to just speak up.
Oh,
yeah.
actually, you do that. You just fold it. You don't fold it.
Yeah, you need to handle them differently in different K-maps.
Each like for you.
Yes, sort of. Yeah, you have really folded the 6-variable function into this 4-variable K-map. And once you get to this point, we just have to interpret them into some output values. So E means output is 1 when E equals 1. So output equals E when you are at that position.
Okay.
Similarly over here, this means output is 1 when B is 0, C equals 1, and A equals 1. Yeah. So when you see an A variable over here, that means B equals 0, C equals 1, output equals A. Output equals A. Or you can say B equals 0, C equals 1, A equals 1, output is 1. So A is just a condition. F equals A, the output depends on that variable. And the output is going to be the same as that variable, given that B equals 0, C equals 1, the position of the A variable.
But 0, 1 just changing?
So you have a 3-input function, A, B, C. Right? Let's say you fix the value of B and C to be 0, 1. At that point, the output depends on the remaining variable, A. Oops. And by the way, I also have the cheat sheet at the bottom left corner, and that is the unfolded function. If you want to get some reference from that golden truth, feel free to do so. Anyone else needs a bit of help? Leland, how do you feel? Hamza? Do you have any ideas how to handle these variables?
I mean, I don't know.
Yeah, that's a very nice starting point. Let both of them go away.
And then I guess you're.
Yeah.
I just.
Yeah, that's perfect. Yeah. All right. So time is up. Before we get into the group discussion, let me just point out one thing from this expanded K-map, right? To set the golden truth right. Oops. Sorry, I accidentally folded up my laptop lids. That's the danger with folding. If you fold too much, it's going to be a difficult life. All right. So from this unfolded, like fully unfolded K-map, assuming that you can do that, let me first point out what is the golden truth, what is the expected minimal expression. And it would be f equals a prime b plus bc prime plus the singular a b prime c. Right, this is what I should get as a minimum expression. And I should also get this expression at the end of this MEV handling the unfolding procedure. All right. So now I would like you to talk in groups of 2-3 people and discuss with each other how you think about this problem, what kind of assignments you make to each variable, each K-map, and if you have already found the minimum expression, also share with each other. So please, if you can get into groups of 2-3 people. All right. Yeah, I think, yeah. Please. So the empty space is zeros in your worksheet? Okay. 0. Yeah, so 0 is always 0, and 1 becomes don't care when you're handling some kind of the MEV dependent scenarios. And then in those scenarios, the MEV get assigned to their corresponding values. Did you run into any difficulty? Or you just mastered it? All right. What do you think about the first scenario? When you put both A and A prime to be zeros, isn't it a bit weird? Yeah.
Setting it to 0. If you keep them, if any of them.
Yes, you do, right? Yes, we do. Even though, numerically, a variable cannot be both 0 and 1, but in this case, we're just trying to find something that does not depend on that variable. So both of them go to 0, so they get ignored. Yeah. What did you find?
That's probably
0 is always 0, 1 is 1 in the independent case and becomes don't care in the other cases. And then we just assign the MEV to their corresponding value. Yeah, very nice. And you do get the same expression, I assume. Yeah, very nice. Yeah. All right. What about your group? What did you find? Yeah, I see.
The answer.
Yeah, I think you got the right answer. Did you run into any difficulties or anything concerning?
I forgot to.
I see, I see. Yeah, I'll give you another 30 seconds. I think you people like discussion a lot. We should have more of this. So yeah, time's up. Let's come together and do this just on the board. I think all of you got the correct answer. So 0 is 0 in all three K-maps. It's always 0, independent of the MEV. So 0 is all 0 in three K-maps. I mean, you can work vertically, one K-map at a time, or you can work horizontally, the same variable across the three K-maps. It's up to you. Right. One can be covered in the independent case, and it could be covered but don't have to be covered when we're looking for implicants dependent on the MEV. And A and A prime both become 0, 0 in the first K-map because we don't want the output and the implicant we find to depend on those two variables. And in the second K-map, when we're looking for things dependent on A, so A becomes 1, A prime becomes 0. Third K-map, dependent on A prime, so A prime becomes 1, A becomes 0. And then we find the minimum expression from each function. Right. In this case, there's only a single implicant in each function, and then we just collect everything. From the first K-map, I get BC prime, which does not depend on the A or A prime variable. From the second K-map, I need to multiply whatever I find with A. So B prime C gets multiplied with A, and in the third K-map, I have A prime times B, which is correct, right? The same minimum expression as I found from this larger K-map. Again, in this case, it doesn't make much sense to go through this MEV method because you can represent the three variable function. You typically only use it if you are looking to represent more variables, like more than 4 variables in a 4 variable K-map. Right? But I think as an illustrative example, this one serves the purpose. All right. And that's everything about MEV. Essentially, again, we fold up a function for compact representation, and then we unfold it to get full utility. And in many of these scenarios, we get to not only a correct expression, but also a minimum expression. In the workbook, you're going to try out some more complicated examples. For example, so let's say in this K-map, suppose I have a variable x over here, right, in the 3 variable K-map. And in this case, if I try to fold it across the middle line, 1, 1 becomes a 1. What does 1, 0x become? Yeah, 1, 1 is a 1. What does 0x become? We don't know. We don't have a solution yet. You can call that a 0, right? It's valid, but you're losing minimality, potentially. Right? Because sometimes you might want to cover this x, use it as a 1 to find the minimum expression. So you can treat the x as a 0, put down 0 in the folded K-map, which gives you a valid but non-minimal expression. What about you treat it as a 1? You could, right? And 0, 1 will be folded into the a variable. And again, you get a valid expression by treating x as a 1, but you may not get the minimal expression. It really depends on what I need for that x in the final function. And in the workbook, you're going to explore a solution to this problem. Really, with some more careful design, you could design an algorithm that guarantees minimality in the presence of more complicated folding conditions. So with that, we concluded our discussion about K-map. Actually, that's how the minimization algorithm we'll see in this class. We have seen minimization using Boolean algebra, using truth table, using K-map, using the QM algorithm, and right now using an enhanced format of the K-map to support larger functions. All right. Up until this point, do you remember what we're optimizing for? What is the optimization goal in general? Yes. To use less materials. And in terms of the Boolean expression, what does it correspond to? Less literals, yeah, fewer products, fewer implicants, and fewer literals. By fewer products, I mean we use a minimum set of implicants. By fewer literals, I mean using only prime implicants. And those are actually concepts in two-level circuits. Right? We can be dealing with two-level SOP, POS circuits all the time. And oftentimes when we do even Boolean algebra conversion, we ask you to convert something into a two-level SOP. All right. And today we're going to see some multi-level circuits. And I want to talk to you in general what we care about when designing circuits in real life. Optimization objective is a complicated equation. Usually people care a lot about area power delay, called ADP. These are the performance measurements. Area is how big your circuit is. Power is, as the name implies, power consumption. How many watts does it consume? And delay is the latency between inputs and outputs. And when we translate that in real life, area corresponds to how expensive the chip is. Power corresponds to whether it's a desktop or a laptop or mobile device, processing units. And delay is like the clock frequency. And of course, you want low area, like very cheap chip, low power, so that it can be cooled down more effectively, gives you more performance out of the power budget, out of your battery, and very fast processing speed, which means low delay. And over the years, this diagram shows you from different technology nodes, 7 nanometer, which is like 2-3 years ago, or maybe 5 years ago, until 130 nanometer. This is about 20 years ago. And you see, from back then, the area has going down dramatically. These numbers represent the feature size of a semiconductor device, right? Essentially the gate length of a transistor. And the smaller you can make it, the smaller your circuit can be. What about, let's say, what about energy? Well, energy is going down in this gray line, it's going down, but not as quick as how the area goes down. What about delay? Well, delay is also going down, but it's just barely better than before. So we're not really making our chip much faster, but we're making it a lot smaller and much more, quite a bit power efficient. And in particular, if you compare if you compare area and energy, area is going down quicker than how energy goes down, which means your energy or power density is going up. Within the same given area, you're actually having more power consumption, which translates to more heat. And that raises the question of what people call dark silicon. When silicon, like semiconductor chips, are running nowadays, some of it is having a very high power density, is doing all the work. The other half is probably just idling and not doing much. So you get this imbalance in power density across the chip. And overall, your power density is also much higher than 20 years ago. And that raises all the cooling issues. So nowadays, power could even be the #1 design consideration. And area delay, those are still important. But power, I would say, is more important to support these application-specific products. For different applications, you have different power budgets. You really need to optimize power to get a good enough battery life, or to be able to cool it down in a desktop device. And these three objectives, of course, it would be nice if you can have all three, but in real life, that is a trade-off space. You can get, let's say, good area efficiency, but mediocre power and delay, or you can get a very nice power consumption, like very low power, but you probably have to put down more devices, and you also don't have the great performance. And this problem is called design space exploration, to explore in this 3D trade-off and to find the best design points. And that is, again, a very complicated question. People use genetic algorithms, or nowadays even machine learning, to solve this problem. But still, just finding the good trade-off point is, in general, very difficult. And you have to run a lot of implementation trials to synthesize or implement the circuit and the different constraints until you find the one that satisfies all your requirements. And this trade-off in design spaces happens not only at the design time, but also during execution. When the chip is already fabricated and then put into a computer or a cell phone, you can still make trade-off between power and performance by scaling the voltage level. It's called dynamic voltage frequency scaling. That allows you to make, again, trade-off between the performance and power when the chip is up and running. It happens all the time. When you open a new app or a new website, your processor is just running at a higher clock frequency for a few seconds before coming back to the idling frequency. And you can get some power saving when the processor is running at a lower frequency using DVFS. All right, and we're not going to care about any of those in this class. We care about like a basic combinational or sequential implementation. And the way we measure delay and area is as follows. So given a circuit, you can easily count the number of gates. Starting from that Boolean expression, you can hierarchically decompose it. At the top level, it's an OR function between h and another function. The next function is the AND between two sums. So you can keep decoupling it, or keep decomposing it until you reach individual gates and individual variables. At that point, you have the circuit, and you can count the number of levels between inputs and outputs. And that determines the latency of this combinational circuit. Whenever you're sending some input value, they have to go through these 4 levels of gates before reaching the output. At each level, we need to suffer some signal delay. And therefore, you can call this having like 4-level delay overall. In our 2-level circuits, we have only 2 levels of gates. And that is the best. That is the best method while still being able to implement any circuit. Remember, sum of min terms, some product of max terms, those are canonical forms. And you can also implement any circuit using SOP or POS. But you can also sometimes go to more levels, 3-level, 4-level, 5 levels, to get fewer gates and hope them to also consume less power. And that is a trade-off we can make by manipulating the Boolean expressions. And transistors, just in general, have different costs. Here's the actual cost to build each gate. AND OR takes about 6 gates for a 2-input gate. 2-input NAND NOR actually only take 4 gates. Right? So it's saying that we're dealing with AND OR, but when you build them as a circuit, NAND and NOR are actually more effective. Right? They cost fewer transistors, so therefore smaller of an area. And the reason is really because CMOS devices are more easy to deal with negation. And therefore, these negated gates, NAND NOR is more efficient than AND OR. AND OR actually just NAND NOR plus an inverter at the end. An inverter takes 2 transistors. Therefore, you have 2 more transistors from the AND OR gates. Right? You don't have to remember any of those. Right. So here we're coming back to a more concrete example. 2-level circuit, you get the best performance. 2 levels of gates is the minimum you need to have still quite a bit of expressive power. And in this case, we can count the delay and the area complexity by counting number of gate inputs or the number of transistors. So to analyze the delay, we need to find the critical path, the longest path connecting the inputs to outputs. In this case, it's going to be going through this inverter, through the bottom gate, and then come back to the final OR gate. That is the longest path that goes through 2 gates and 1 inverter. And let's say inverter have a 5 picosecond delay. A gate, any other 2 input, 3 input gates have a 20 picosecond delay. We would have 5 picoseconds here, 20 picoseconds here, 20 picoseconds here, which gives you a 45 picosecond delay overall. So let's say you have a 1 gigahertz processor. You essentially have 1,000 picoseconds for each clock cycle. Right? If you have a 5 gigahertz processor, you have 200 picoseconds. So actually, real-life circuits are typically somewhere between 15 and 20 level, maybe 13 to 20 levels. That's a pretty accurate number for real-life circuits. So we never design 2-level circuits just because it's too complex. We can do things more effectively, and also by hierarchically constructing these data path components like multi-bit adder using current look-ahead, using multiple levels of current look-ahead to more easily build circuits. So real-life circuits are typically multi-level. Right, so this small circuit has a 45 picosecond delay. Right, what about gate inputs? Gate inputs is an easy measurement of the area. Right, you can, of course, count the number of transistors, but gate inputs gives you a pretty good idea. What I mean by gate inputs is you sum up the number of inputs to each and every gate. So this gate has 3 inputs. This one has 3 inputs, 3 inputs, 3 inputs. Inverter has a single input. So you have 13 gate inputs in total. It's an estimation for the area. And you can sort of do comparison between 2 implementations based on the number of gate inputs. In terms of transistors, right, you have to sort of look at this table. But don't worry about it. We'll just do it together. I'll not ask you to count the number of transistors in any questions. All right. So this one has 8 transistors, 8, 8, 8, and 2, which gives you 34 transistors in total. Right. So that's how I count the complexity of this 2-level implementation. And to go from a 2-level to multi-level implementation, we can look at the Boolean expression and then apply distributivity. Distributivity allows you to factor out certain components from multiple parts. And when you do factoring out, then that one becomes a 3-level implementation. Again, when you count 2 level, 3 level, we sort of don't worry about the inverter. That expression, you see C prime plus C prime dot D dot sometime requires an additional OR gate. So overall, this is a 3-level circuit. And again, we can apply the same analysis of gate input counting, delay counting, and transistor counting to see which implementation is better. In this case, so let's say the delay would be going through these 3 gates, which gives you 20 picosecond times 3, which is 60 picoseconds of delay. All right. In terms of gate inputs, I have 2 here, 3 here, 3 here, 2 here, 1 here, right, which is 11. 11 gate inputs. And in terms of number of transistors, I have 6 here, 8 here, 8 here, 6 here, 2 here, which is 30 transistors. I hope I'm doing my math right. Is that right? Right. 11 gate input, 30 transistors. Before, you have 13 gate inputs, 34 transistors. So we do get a bit of saving from this multi-level implementation, but at the cost of a higher latency. Now, every signal has to go through 3 levels of gates before reaching the outputs. Again, you're making a trade-off between performance and area. You can do factorization in a different way. Right? This distributivity can be applied to a different set of terms over there. Right now, I'm only factoring out A from the first and the third impedance. And the bottom one shows the circuit implementation for that. Again, if you do gate input counting, you have 2, 2, 3, 2, 2, 2, 1, which is 14 gate inputs. All right. And if you do transistor counting, you have 6, 6, 8, 6, 6, 6, 2. Oh, what is that? 46 transistors. This is worse than the implementation on the left. It's actually also worse than the two-level implementation. Right, so sometimes when you apply distributivity, you get lower performance and also a higher area, which is worse in every aspect. Right. And if you compare these two implementations, one you can probably observe is that the left expression makes a better use of this resource, A plus B. It's actually trying to factorize two literals from two impedances rather than one literal from two impedances. So this one encourages a higher level of reuse of some computation. That one has a bit of reuse, but you're not really saving much, but you're also spending a little bit more by expanding it into more levels. So in general, the more reuse you can do, the more sharing you can do, you get a more optimal implementation in terms of area. It's not guaranteed. This is like a very ad hoc solution, but just in general, try to do more sharing. Right? When we do logic minimization, we were doing sharing. We let two minterms share the same impedance, right? Or multiple minterms sharing the same impedance. It's actually the same idea over here. If you can let multiple impedance share the same hardware implementation, you can sort of get some saving. All right, so we have just done several implementations based on the SOP expression. You can also implement any circuit using a product of some form, right? OR gate followed by an AND gate. And between SOP and POS, there's also no clear winner. Either one could be the better implementation. You really have to try both to figure out which one is better. So let's say in this POS two-level form, I have 10 transistors over here, 6, 6, 6, 6, and 2. So 24, 26, 36 transistors, which is not as good as the original but SOP, but it's not bad. It's like an all right implementation. When you do factorization, you can factor out BC prime. So this one and this one can be combined into A plus BC prime by applying that a little bit of a unnatural distributivity that is only true in Boolean algebra. And then that one will also translate into a circuit implementation. You have 8 over here, 6, 6, 6, 6, and 2. So 24, 26, 34 transistors, which is a little bit better. Right? And how do you figure out which one is the best? There's really no method. You probably have to try all these combinations. And that's really the complexity of design space exploration. There's so many different ways you can implement the same function. And it's unclear which one gives you the best performance, area, latency, until you have implemented it. Right? And I wouldn't expect you to be able to find the one that has the minimum number of transistors. That's just not a reasonable task. I just want you to appreciate that we can apply distributivity to convert a two-level into a three-level, sometimes four-level circuit, and then be able to analyze the complexity of these circuits. Yeah. Any other questions? Yeah, any questions about this multi-level? Essentially, we apply Boolean algebra and then put down the circuits, do a counting of gate inputs or transistors. We get to see which one is more complex. Right? Usually, two-level gives you the best performance. Multi-level can sometimes save you a bit of area by doing the most reusing and sharing. All right. If there's no question, we're going to move on to the next topic. We just said that NAND NOR are cheaper than AND OR gates. So oftentimes we prefer to implement a circuit using NAND and NOR gates rather than these alternating AND OR gates. A very brief recap of what NAND gates and NOR gates do. So NAND gate is the inverted AND gate. This is a truth table or K-map. And then NAND can be represented using a few different symbols. That's the regular NAND symbol. It's also AND followed by inverter. Some people also represent a NAND gate using this symbol, an OR gate with two inverted inputs. And that is indeed a NAND gate. So let's say if I connect my XY to the bottom gate. Right, what I'm doing is I'm doing X prime. I'm doing X prime plus Y prime, which is the same as XY complement by De Morgan's theorem. So an OR gate with two inverted inputs is also a valid symbol for NAND gate. In this class, we use the first symbol most commonly, but actually in industry, people use this symbol a lot. I don't know what's the reason for that. Just a little bit cooler. Right? You describe NAND as inverted AND, it's like too normal. You use an OR with two inverted inputs, well, you're very cool. And people call this bubble pushing. You can go from top to bottom by pushing the bubble, like conceptually, pushing the bubble backwards through the gates. In the meantime, it becomes a bunch of bubbles at the gate inputs, and you're also switching the gate between AND and OR. So push the bubbles through the AND gate. The gate becomes an OR gate. You have multiple bubbles. You can also think about bubble pushing in a different direction. Two gate bubbles, you push it through the gate. This one becomes an AND gate. All the bubbles converge into a single bubble. So the bottom to the top through bubble pushing. Similarly, NOR gate can be represented as OR gate with inverted output, or in this cooler way, AND gate with two inverted inputs. Right? Again, think about bubble pushing. Bubble through the gate becomes a bench bubble, changing the gate type. And again, you can prove the bottom one is indeed correct by applying De Morgan. Right. So you may say, well, now we're seeing these two gates and trying to just implement any circuit using these two gates. Is it going to be an entirely new task? And the answer is no. Once you get a SOP, some alternating AND OR circuit, you can directly convert that into a NAND NOR circuit without any complexity. And here's how we do it. The idea is a two-level sum of products can be represented by two levels of NAND. It just works. But I have to be careful with a few things. To approach this proof, you can think of this as a Boolean algebra, or you can pictorially think of it as a bunch of bubble pushing. What I'm going to do is I'm going to put, let's say, two bubbles at the output, right? Like, actually, it's shown at the bottom. Two bubbles through involution doesn't change your function, and then we push one of the bubbles backwards through this OR gate. So the gate becomes a NAND gate with three inverted inputs. One of the inverted inputs will be caught by this input variable to become an inverted input variable. The other two inverters can be propagated further upstream to connect with the previous gates, make those gates NAND gates. So now you have an equivalent NAND-only implementation of an SOP circuit. Alternatively, you can think about this bubble pushing game as inserting a bunch of inverters at the middle. And then one of these inverters will be put next to the previous gates. The other inverter will be propagated through the gate, will be pushed through that OR gate to make it a NAND gate with inverted output. And always remember here you have like a standalone variable, so the variable also needs to be complemented. Right. And some people memorize this as a rule, which I would really recommend against. Some people say, well, the way we do it is for two-level circuit, we don't flip variable over here, we flip the variable over here, we just replace everything with a NAND gate, and then that gives you a correct circuit. That is true. That is a correct conclusion. But I expect you to be able to do this like the more manual analysis so that you can handle a wider range of circuit conditions. Similarly, a two-level product of some circuit can be converted into a NOR-NOR circuit. Again, we do bubble pushing. Two inverters at the output by involution. One of the bubbles pushed through the gate becomes an OR gate, and then 3 inverted inputs. So those inverters can be connected to the previous OR gate. So 3 NOR gate, and you still have 1 inverter left at the end. That one can be put together to create a NOR gate. Right. You can also do that in the middle level, and then only push the inverters towards the output. So we talked about two-level SOP or POS, and here's how we convert each of them to the corresponding NAND or NOR-only circuit. And remember, product of sum can only be implemented in this NOR-only format. Sum of products will translate into a NAND format. Yeah, there's no easy way to switch between them. You cannot use NOR gates to easily implement SOP. Right? Simply because when you do bubble pushing, this is what you'll naturally get. If you want to get everything to be a NAND gate, you have to do a lot of transformations. Bubble pushing doesn't naturally give you a NAND-only circuit for this POS. We also talked about multi-level circuits just a few minutes ago. And as it turns out, you can also translate that into a NAND-only circuit. Okay, my original circuit has this alternating OR and OR and OR. What you can do is you can start from the output. For every 2 levels, you apply the regular 2-level conversion method. Change out the gates. You have inverted inputs over here. Keep the original inputs over here. And that's it. That's how you handle these 2 levels close to the output. And for the next 2 levels, you just think of it as a separate 2-level circuit and then apply the regular conversion rule. Right, essentially, every 2 levels, I'm going to draw a cut line. Every 2 levels, we follow the regular 2-level conversion algorithm. And together, they allow you to make a multi-level conversion. And again, at level 5, keep in mind that this is an odd number of levels. So I need to flip all the input variables. So really, when I do the bubble pushing, all of these inputs will also be complemented. Yeah, any questions? All right. Here's, again, an exercise for you. Please try to convert this to use only NAND gates and see what you get. Again, this is not a very elegant 2-level circuit, right? It has like 3 levels, and they sort of like go in this kind of fan out and then reconverging pattern. But again, try to apply this bubble pushing idea to convert this into a NAND-only circuit and see if it's feasible. Hint, it may not be feasible. Or not feasible without some additional transformations. Yeah, I'll give you 2 minutes to work on this exercise before talking with your classmates. I'm going to put down some hints on the side. This OR gate, the same as a NAND gate with some inverted inputs. Yeah, actually, I think this one allows you to add inverters, and with additional inverters, it should be doable. All right, time is up. Could you discuss with people around you to see what you find, or even with some partial findings, share with each other how you approach a problem, and for example, starting from which gate you do the conversion first. Yeah, feel free to get into group discussions once you are ready. So this OR gate is the same as like NAND gate with 2 inverted inputs, right?
Yeah.
So A would be kind of like inverted,
Yeah.
and B would be inverted, and then this one would be like a NAND. Yeah. One will be turned into a NAND. I think I missed the invert over here. So where did you start? Did you start from the OR gate on the left? You start on the right. So start on the Z output, and then sort of like introduce 2 inverters over here, and then propagate one of them backwards to become an AND gate with inverted inputs. Right? That's how we kind of like put the inverter over here, and then add another inverter at the bottom. Right? Yep. I think that's very nice. I also like to start working from the output and only push bubbles towards the left. That's essentially how that multi-level, the 5-level example works. Like output, that's how you count level 1, 2, and level 3, 4. Yeah, keep discussing. I'll try to explain to each other how to think about the problem. Ron and Judy, did you discuss?
Yeah, I'm still not sure. So I originally put 2 bubbles in here and then I pushed it out, and then I pushed over here, and then I pushed this bubble.
Oh, I see. That's a very good point. So actually, you still have a bubble here.
Yeah.
You cannot convert this bubble to be a bubble there. There's like a fan node, like a branch. And you have to sort of have bubbles on both lines to be able to do further propagation. If you only have bubble on one side, that is different from having the bubble on the stem. And I say I call this Y. So this one is a Y, this is a Y prime. If you put the bubble at this line, you'll have Y prime on both sides, which is a different function. So bubble pushing, on a wire, you can put that at the end, at the beginning. On this kind of branch condition, you cannot push like only one bubble towards the stem.
Push it from A to B.
You could, yeah, if you have a bubble over here, you could eliminate it and put 2 bubbles. You could. I think it's easier if you think of this as like a 2-level sum of product form. Think of this as like a separate circuit, another 2 levels, in that 5-level example. Right? Think of that as a standalone OR gate and handle it by itself. And then handle these 2 using the regular 2-level conversion rule. Right. What did you find? Yeah, I think you almost get it right. I don't think you need the invert over here. I think there should be a wire. Yeah, change it to a normal wire should give you the correct answer. And I see what you get. Yeah, I think it's probably right. Like even though this is not a NAND gate, but I think it looks like a valid conversion. Yeah, and with inverted outputs. All right, guys, we'll just do it together. We're almost at the end of the lecture, so I'll just walk you through the process. The way I do it is I think about these two as like a two-level sum of product circuit, and I apply the normal conversion rule. So I'll draw the circuit on the side. I first put down an NAND gate for Z with some inverted inputs. Well, actually, I'll draw it on the original diagram. I think it's easier to see. I convert this into a NAND gate with two inverted inputs. So one inverter on top, which I put next to the AND gate, another inverter at the bottom. And I'm essentially done with these two gates. They're already converted into a NAND format. And this inverter at the bottom actually cannot be propagated any further, because on this branch, you have inverter on one side, and you have no inverter on the other side. And having an inverter on the branch is not equivalent to having an inverter on the stem, the kind of point before fanning out. They're different. So that inverter cannot be pushed any further. Or if you want, you can add another inverter over here, and then like essentially double inverter to push it any further. But it's also not helping me, because the next gate I need to handle is this OR gate. And the OR gate can be viewed as something sitting by itself, and you can convert that into a NAND gate with two inverted inputs. And essentially, these two inverters will just be represented as inverters. And now you have a fully NAND circuit. And of course, these two inverters over here and over here, they can also be combined into a single inverter. So rather than drawing this inverter, you can create another branch after the inverted A line and then connect it to the bottom. Right. Try to sort of follow this, every two level, do the conversion within that two level, so that every, starting from every OR gate, you have a fresh conversion run. Right. And one thing to keep in mind is how to handle these kind of branches. Right. Inverter on this side, no inverter, they cannot be combined into an inverter before the fan-out point. All right. So as a summary for today, we talked about mapping the variable to fit a larger function into a smaller K-map and still do logic minimization. We then talked about some alternative implementation styles other than two-level SOP or POS. We talked about multi-level circuit by applying distributivity. We also talked about NAND NOR conversion for two-level and multi-level circuit through bubble pushing. And that's everything for today. Is it okay if I spend a few minutes talking about these statistics? I'm going to have two slides over here. Oops. Sorry, again, I keep folding my laptop. All right. So here's your survey result on lecture efficiency and workbook efficiency, which I really like. People generally find both of them to be quite efficient, particularly the workbook, which is where I think most of the learning happens. I hope most of the learning happens in the workbook, not just when you work on the workbook, but also when you check the solutions, read our feedback, and then really develop a full proficiency on the material. And then I really hope that everyone can check all the workbook solutions, because getting full points doesn't really mean you really understand all the concepts. For one thing, we have those graded by completion questions, but also sometimes by reading through our explanation, that gives you a slightly different perspective. And sometimes this alternative perspective helps you to understand the material better. People generally don't do much preparation before coming to the class, which I think is all right. You can make different trade-offs between pre-class preparation and post-class review. But if that's the case, make sure to spend a little bit more time after the class to make sure you're fully ready and fully familiar with the material before working on the workbook. Again, just being able to solve the question also doesn't really mean that you have achieved full proficiency of the material. And again, I want to remind you, this is what I think learning should happen. Specifically, that learning loop, getting support, and then reading the solutions. It's very essential to develop a better understanding of the material. And again, the other thing is you also have the option to replace the midterm with your final score. You don't have to tell me. I'll just automatically pick the best between the original scheme and this, 40% on the final scheme. The higher of the two will be your final grade. Yeah. Yes. Okay. Yes. I think, Eric, you do have an extra inverter before the top NAND gate, right, in your solution. Oh, this one, like to sort of like both sides?
Yeah.
I see.
No, I didn't do it both sides. I propagated.
Oh, got it. Got it. Yeah.